Now we want to move on to talk about the integral of a vector field over a surface. When we did that with line integrals, what we did was we wanted to take the integral over some curve of f dot ds. We turned that into an integral over that curve of f dot the tangent, the unit tangent to that curve, and we integrated that new scalar function over the curve using the original line integral, the line integral of a scalar function. We want to do essentially the same kind of thing here. Except, unfortunately, when we look at tangent vectors to a surface at a given point, if we have some surface here and we have a point on there, there's a lot of different tangent vectors. All of these could be tangent vectors to that surface at that point. So we can't just use tangent vectors because we would have too many options to narrow it down. Instead, what we're going to do is look at normal vectors. We're going to look at the vector that's perpendicular to the surface at that point and use that dotted with our vector field and integrate that one over the surface. But unfortunately, we do hit a little bit of a snag there that we need to deal with before we can actually get into the surface integral. Let's look at a particular parameterization. So we'll have x equals 2 plus s times cosine of t over 2 times cosine of t. Y equals 2 plus s cosine of t over 2 sine of t. And z equals s times sine t over 2. And let's look at the graph of that thing. Alright, so we're looking at the surface. S component is 2 plus s cosine of t over 2 times cosine of t. Y is the same kind of thing, 2 plus s cosine of t over 2 times sine of t. And our z component was s times sine t over 2. Where s, I guess I didn't write down what limits I'm going to do. I'm going to do s from -1 to 1, and I'm going to do t from 0 to 2 pi. We have this surface here. This is a surface that is commonly known as the Mobius strip. So think if you take a strip of paper, give it a twist, and glue the ends together, you get this kind of a shape. So you can label it here. Of course, I said s went from -1 to 1. T went from 0 to 2 pi. Now watch what happens when I put the normal vector in. So I went through, and I'm not going to go through all the steps here, but if we take the derivatives of these with respect to s and t and take the cross product, we get r sub s crossed with r sub t is equal to some pretty complicated thing. Let me write it out here. We have s over 2 sine t minus 2 plus s cosine of t over 2 times cosine of t times sine of t over 2. That's our I component. We have essentially the same thing, but a little bit different for the j component. So this one turns into, we have a negative, we have a cosine, we have this same thing. This one turns into a sine, and this one stays sine. That's our j component. And then finally, our k component is a little bit shorter, but it is still maybe a little bit more complicated than you'd like it to be. We have 2 plus s cosine of t over 2 times cosine of t over 2. That's times k. So fairly complicated looking vector, but we can go ahead and graph it. gone ahead and put in two sliders here for s and t so I can move the vector around. But we'll go ahead and graph a vector where we put the values of s and t into A, and then that'll give us the point on the actual surface, and then we're going to modify that point by adding in what we had before. I'm going to do that off camera, basically. So assuming I typed all this in right, when I press enter, it should give us the normal vector at a point. And let's actually make that stand out a little bit better. So we have it sticking out there. If I move S, if I change my S, it moves in that direction. So these are my S grid lines, or grid curves. That doesn't really change too much. It gets a little bit longer or shorter. We'll actually deal with the different magnitudes. We'll actually normalize them and only look at look at unit vectors eventually. But watch what happens when I change t. As I move along, it just moves pretty smoothly around. But I get back to the same point on here at, what was it? Whatever that point is. I guess that's A of st. If we put that on there, that is the point 200. The point 200 is the same base point for both t equals 0 and t equals 2 pi. But the actual normal vector is pointing in a completely different direction. In a sense, what we've shown here is that this surface only has one side to it. If I take it and flip it over, I haven't changed to a different side. I'm still on the same side because I can get to that side by just moving along the surface without changing the direction of my normal. Whenever something like this happens, we say that this surface is non-orientable. And being non-orientable is kind of an issue whenever we're doing surface integrals with vector fields, because we need the orientation of the surface to actually define the integral itself. So we're going to have to throw these kind of surfaces out. So formally, we're going to say that an oriented surface is going to be a surface S where we can choose we're going to say a unit normal. And we're specifically saying a unit normal because we also make sure that the normal can't just go to 0 and to move to the other side of the surface. Something like that would kind of break things. But that's not going to happen as long as we have a nice smooth surface. But we even want to be able to talk about surfaces that might not necessarily be smooth. So we're being a little bit more general here. We're going to call that in. It'll be a boldface in the text, or an in with an arrow over it if you prefer. This unit normal needs to vary continuously. Over S. So basically, with what I was doing with my normal here, I should be able to essentially move my parameters around, and it shouldn't just suddenly jump to a completely different direction. That's all I mean by it varies continuously. Technically, we could get into the more precise definitions of continuous, but that doesn't really matter right to us right now. Note here that we're going to say that the orientation itself is in. That the unit normal that we've chosen is going to be our orientation. Also note that there should always be two orientations, in and negative in, because negative n just gives us the vector that points in the opposite direction. That's the other direction that's going to be perpendicular to the surface at any given point. We can't really do that with the Mobius strip because these really kind of end up being the same thing, even though they really shouldn't be. Now, if an oriented surface is given by a parameterization for a parameterized surface, or parametric surface, I guess, we have given by r of uv. We can get as long as we have an actual orientation on there, so something that's not like the Mobius strip, where it actually doesn't break that kind of idea. The parametric surface will have a unit normal of n equals r sub u cross r sub v, and since we have to normalize it, we go ahead and divide by its magnitude. This will be the formula that we'll use for the unit normal to a parametric surface, assuming that we do actually have it orientable. If a surface is given by a function, so kind of as a graph, well, a graph of z equals f of x, y, a surface of this form will always be orientable, mostly because it can't really loop back on itself in order to make sure that things don't, so that we can actually swap from one side to the other like we did on the Mobius strip. But in that case, we can actually use the parameterization of r of xy is equal to xi plus yj plus f of xy k. Essentially just leaving x and y alone and using the function itself for our z component. We can follow this kind of idea. Recall that we had r sub x cross r sub y is equal to negative the derivative of z with respect to x times is our I component, negative z with respect to y, or the derivative of z with respect to y is our j component, and then our k component is just k. One nice thing about this is that the k component here is positive. So that means that this orientation is always upward, but we do need to divide by the magnitude, which gives us maybe a little bit more complicated of a expression than we'd like to have. And I'm actually going to go ahead and save myself a little bit of work. So the top here is going to be r sub x cross r sub y, but when we divide by the magnitude, we get the square root of the derivative of z with respect to x squared plus the derivative of z with respect to y squared plus 1. Just the magnitude of what we had on top. But the point here is that we have a nice orientation that is pretty standardized. It's the upward orientation, and we always know that it does have an orientation, and so everything works out very nicely. Let's look at the orientation on the sphere. Let's look at the sphere of radius a. Which we could just go ahead and write as x squared plus y squared plus z squared equals a squared. But what we're going to do is parameterize it using spherical coordinates. So that means that x is going to be equal to a sine phi cosine theta, y is equal to a sine phi sine theta, and z is equal to a cosine phi. In the last section, so in the last set of videos, we did derive a formula for the cross product of r sub phi cross r sub theta, and rather than go through all the calculations again, I'm just going to write it down. So we found that r sub phi cross r sub theta is a squared sine squared phi cosine theta for our I component. We have a squared sine squared phi sine theta for our j component. Finally, we have a squared sine phi cosine phi for our k component. We even took the magnitude of this as well. The magnitude of this, because a lot of the sine squares and cosine squares managed to combine to give us ones, everything simplifies pretty nicely down to a squared sine phi. And we noted back then that this is basically our form that we use for spherical coordinates. This is rho squared sine phi, where rho in this case is a. Well, when we're taking the unit normal, we're going to divide this. We're going to divide all three of the terms of r phi cross r theta by a squared sine phi. But everything has an a squared in it already. That's going to cancel out. And everything has at least one sine phi that's going to cancel out. These two will still have a sine phi in them. The last one won't. So when we divide the first one, we get a cosine theta times I. Sorry, we have two sine phis. I need to leave one of them there. We have sine phi cosine theta. For j, we still have a sine phi. We still have a sine theta. And for k, well, the first part completely goes away. We're just left with the cosine of phi. So a fairly nice formula. Not too complicated. But what is actually even nicer is that if you look at these, what we actually have in here, these are essentially the original x, y, and z components, but except with no radius in them. The a is gone, but we still have sine phi cosine theta, we still have sine phi sine theta, and we still have cosine phi. In other words, the orientation here is just the unit vector that points outward directly away from the origin. You can even kind of say this is kind of x over a I plus y over a. Actually, I'm even going to move the a outside. You could write this as xi plus yj plus zk all over a, or you can even write this as r of phi theta over a. It's the original parameterization, the original spherical coordinates, but without a radius in them. So it points directly away from the origin, and it points outwards. That's kind of the important thing here. At every point of the sphere, this points out from the sphere. And note that it only worked this direction. It points outwards instead of inwards because I did r phi cross r theta. If we did r theta cross r phi, this would actually point inwards. That would be the other orientation. So that which direction the orientation goes will change if I swap the order of my parameters. But the reason why we like to put phi and then theta as the order for spherical coordinates like this, and I mean we didn't do this back when we used it for integration because we didn't care about the orientation so much, but here we are putting the phi before the theta because it is going to change the orientation that we have. And whenever we do have a closed surface, so a sphere is a good example of a closed surface where it actually encloses a volume. Maybe I should actually write that down. So here our sphere actually has a ball inside of it. What we're going to say is the positive orientation. So the one that points outwards. And of course the negative orientation will be the other one. The one that points inwards. So we definitely want to normally we'll want to have our vectors pointing outwards from the sphere rather than inwards. And so the ordering of phi before theta will actually be kind of important to that. Pay attention to exercises there when they actually ask us to do our surface integrals with our vector fields. They are going to specifically ask us to use the positive orientation whenever we notice that we have a closed surface. We'll look at that in some of our examples. But I'm going to go ahead and leave this video here. I don't want to try putting it all in one video. I just want to have a video just dedicated to talking about orientation, because it is kind of an important topic for making things actually work. And it's actually going to be kind of important when we move on to things like Stokes' theorem. If you've actually taken a look at the summary section of 16.10, you might notice there that the divergence theorem is about things that have a closed surface involved, and they specifically draw in the normal vectors that are pointing outwards, because they want us to make sure that we know that we're dealing with a positive orientation in that theorem. So orientation kind of matters here. In the next video, we'll actually talk about what the surface integral of a vector field actually is. So meet me in that one, and we'll get to it.